This is my 8 puzzle walkthrough. This is the application window with our search interface and difficulty interface. We can try running different algorithms, and we'll see the result printed out on the right with the solution path and the total algorithm cost. So now let's take a look at the code. All of these search algorithms inherit from this abstract base class, base search. So when we hit search, this search function runs. We do some initialization of the search and then input the initial node for the initial state and begin the loop. So this is the search loop. Here we get the successor node from our successor function. That successor function just removes the first value in our linked list queue. It makes sure to also remove that value from the queue map and move it over to the explored map. These are used for verifying if a node is repeated, and we don't add repeated nodes. Afterwards, after we get our node from our successor function, we check if it's reached that goal state. If it has, we break out of that loop. If it has not, we expand that node. Here in the expansion, we have our expand children function called on the node object. And this just populates the child nodes for up, down, left, and right, leaving those values null if there is no up child, say in the top left corner node. Afterwards, we calculate the cost. The default value of this is to set the eval cost to the sum cost of the movement to reach this point. And then we enqueue the children if that child is not null and if it is not repeated. And this is where we do that repeated check. We just do a contains call on our explored map and our queue map. If it's not in either of those, we haven't seen this before, and we enqueue that child. So this enqueue function is abstract and is overridden by the search algorithms. Here we have our breadth first search algorithm, which enqueues at the end of the linked list, and then it adds reference to that linked list node based on a key of that state to the queue map for that is repeated check. Since our successor function's dequeuing from the front of the queue and we're adding to the back, this is a first in, first out search algorithm. Here we have depth first search, and its enqueue function is basically the same except we're adding to the front. So we're adding to the front and our successor is removing from the front. So we're having a last in, first out algorithm. Next is iterative deepening, which inherits from depth first search, so we're using this enqueue function from here, and we're overriding the loop function, which is basically the same, except we have this check where we only expand nodes whose depth is less than our search depth, and once that queue is empty, we're going to increment that search depth, clear all the data, and restart the search. Next is uniform cost search, which inherits from our base search. It's going to only override enqueue, and it will insert the node in sorted order based on the eval cost. So when our successor function removes from the front of the queue, it's going to be removing the node with the lowest eval cost. All the following heuristic search algorithms will inherit from uniform cost search. So they'll be using that enqueue function and just overriding the calculate cost. This is the A*3 search, which just uses a combination of the Manhattan distance and the number of values not in position. It applies a 50% gain on the total Manhattan distance from goal positions, sums those two values for the H cost, and uses the h cost and sum movement cost to get our eval cost.